Page 98. Let's draw some Lewis structures or lined bond structures of covalent compounds. There's a procedure here on page 98 for drawing fluorine, but we'll just jump in and start here with chlorine, oxygen, nitrogen, and so on down the list. Let's start with chlorine. I'll start by writing the formula, and we need to keep track of how many electrons we should see in the structure, so let's write down the group number. Chlorine's a halogen in group 7A. Each chlorine atom brings 7 valence electrons. There are 2 of them. That should see 14 valence electrons in my structure. Now, what type of bond do we expect to see? Generally, we want to consider the electronegativity values. Chlorine is 3.0, but it doesn't really matter because it's bonded to itself, so it has to be a nonpolar covalent bond. But we'll do this just once. Delta En for the atoms being bonded together, chlorine to chlorine. 3.0 minus 3.0 is 0, and that is a non-polar covalent bond, which means that the molecule must also be non-polar covalent, which means that it will be insoluble in water, because water is a polar solvent. Like dissolves like, so water dissolves polar solutes, but not nonpolar solutes. So chlorine has a very low solubility in water. It's in the part per million level. Let's draw the structure. We'll start with the Lewis symbols of the atoms. Group 7A elements have 7 valence electrons. This is a covalent bond, which means electrons are shared. I'll just draw them coming to the middle. This occurs when the 2 chlorine atoms move together and overlap their valence shells and electrons are shared. The structure we draw would look like this. This is the line bond structure or Lewis structure of a chlorine molecule, Cl2. We said we should see 14 valence electrons in it, so let's keep track of that. We'll add up the bonded electrons plus the non-bonded electrons, add them together, and that'll give us the total number of valence electrons. There are 2 electrons in every bond. That means there's 2 bonded electrons, 2, 4, 6, 8, 10, 12 non-bonded electrons for a grand total of 14. And good, that agrees with what we determined. So this is called a single bond, obviously. A single bond is also called a sigma bond. And this term here, sigma, is the Greek letter for S, lowercase. In statistics class, that's the symbol for standard deviation, but in drawing structures, that's a sigma bond. So every bond contains 2 electrons. Let's look at an animation of chlorine molecule. So it's a linear molecule. These animations do not show non-bonded electrons. It shows a single bond between 2 chlorine atoms. Chlorine is a pale green gas, so in the animation it's green. Let's draw oxygen next. Oxygen is another diatomic molecule. It's in group 6A. Each atom brings 6 valence electrons, and there are 2 atoms, so that'd be 12 valence electrons to find in our structure. Again, it's a nonpolar covalent bond because oxygen is bonded to itself. Therefore, it would be nonpolar and insoluble in water. And in fact, the solubility of oxygen in water is only about 9 to 10 ppm at atmospheric pressure, and room temperature, which is pretty low, Rather amazing that such large sea creatures can live and extract enough oxygen to survive at such a low concentration, and it's even slightly lower in seawater. In any case, we draw a Lewis symbol of the two oxygen atoms. And we see that oxygen needs to share 2 electrons. And of course the guiding principle here is that the atoms will bond in such a way that they all complete their valence shell or empty the valence shell to become isoelectronic with the nearest noble gas. In this case, each oxygen is becoming isoelectronic with neon. So that's the correct line bond structure of oxygen. We have bonded electrons, non-bonded electrons, valence electrons, 4 bonded electrons, and 8 non-bonded electrons for a total of 12. And that agrees with what we calculated. So oxygen has a double bond. And a double bond is made of 1 sigma bond plus 1 pi bond. We'll go into the difference in more detail later, but for now let me say that a sigma bond has electron density immediately between the 2 nuclei of the atoms that share the electrons, whereas a pi bond is just outside that space. Let's look at an animation of an oxygen molecule. Here we see the oxygen to oxygen double bond. The next molecule we're asked to draw is nitrogen. Nitrogen is a diatomic molecule, N2. Nitrogen is in group 5A. Each atom brings 5 valence electrons. We should see a total of 10 valence electrons in our Lewis structure. This will also be a nonpolar covalent molecule, which will have low solubility in water, typically in the ppm level. You'll notice as I draw these structures that all of the unpaired single electrons, all the unpaired non-bonded electrons, always form bonds. And that is almost always true, and it certainly will be for now. So plan on a structure at the end that has no unpaired electrons left. And then each atom should have a valence electron configuration that's like the nearest noble gas. So that's the molecule of nitrogen. So bonded electrons plus non-bonded electrons together make valence electrons. So we have 6 bonded electrons and 4 non-bonded for a total of 10. Right. This is a triple bond. A triple bond is made of 1 sigma and 2 pi bonds. Only 2 elements on the periodic table can form stable triple bonds, carbon and nitrogen. Is it clear in what way these nitrogens now have full valence shells? Let me draw a circle around this nitrogen. So in its valence shell, it has a total of 8 valence electrons by virtue of sharing 2, 4, 6, 8. Likewise, the nitrogen on the left in its valence shell also has 8 valence electrons. So they are both isoelectronic with neon. And so it's stable, and nitrogen is a very stable compound. Let's take a look at an animation of nitrogen. Well, maybe not too exciting, but it certainly shows the nitrogen to nitrogen triple bond. The next molecule we want to draw is a water molecule. That's H2O. Hydrogen is in group 1A, oxygen in group 6A. Number of valence electrons, 1 times 2 for the hydrogens plus 6 is a total of 8 valence electrons. Now, this is the first time we have 3 atoms in a molecule. We need to know what is connected to what before we can determine the polarity of the bonds. So the question is water bonded like this? Or is it bonded like this? Now, I know it's trivial because you know, but there's more than just memory here. The first example is wrong. Why is it wrong? Why is that not it? Because hydrogen can never be central. Hydrogen can never have 2 bonds. It's got to always be on the end of a structure because it only has 1 valence shell to share electrons and forms a single bond. So now we know that the arrangement of electrons is hydrogen to oxygen. Let's calculate the difference in electronegativity for that. So the electronegativity values for hydrogen is 2.1, oxygen is 3.5. So the difference in electronegativity for an oxygen to hydrogen bond is 3.5 minus 2.1 is 1.4. What type of bond is that? Let's check our table. So on the lower scale, non-metal to non-metal, 1.4 difference falls in the polar covalent range. So in fact, these are polar covalent bonds. Let's draw a molecule. Here, this is PC. Okay. So hydrogen, I'm going to draw this bent because water is bent, and you'll learn why later in this course, but not just now. So I'll just join them like that. Not very tidy. There, that's a water molecule. How many electrons are in it? Bonding electrons, non-bonding electrons, valence electrons. Bonding is 4, non-bonding is 4, total is 8. 8 is what we calculated over here, that's good. The electrons are not shared equally between hydrogen and oxygen. We can draw a dipole arrow for polar covalent bonds, and we only draw them for polar covalent bonds, and they point in the direction of the more electronegative atom. The hydrogen is slightly positive, partially positive, and the oxygen is slightly negative, and these dipoles are additive. If you combine head to tail, they combine together and oxygen is quite negative. If we were in physics class, we could talk about vectors and combine 2 vectors together. Let's say we added this vector with this vector. The resultant vector is from the head of the first to the tail of the last. This would be like the net dipole. Yeah, so the dipole doesn't cancel. Water is a very polar molecule. So polar covalent bonds could cancel, as we'll see in some cases, but in this case the dipoles don't cancel. I'll say they're additive. And so water is a polar molecule. The geometry of the water molecule, I mentioned that it's bent, as I've drawn, and we'll discuss that more in the next chapter. The term for this is the molecular geometry. The molecular geometry is the arrangement of the atoms around the central atom. So how are the hydrogens arranged compared to the central atom? We would say it's bent. Some books use the term angular, and I've seen in some books they say it's V-shaped. They all mean the same thing. In the case of the water molecule, the bond angle is about 105 degrees. Again, more in the next chapter, why that is. Let's take a look at an animation of a water molecule. So the molecule definitely is bent. Next, we want to draw an ammonia molecule. Ammonia has the formula NH3. So that's group 5A and group 1A. 5 electrons plus 1 times 3 is 8 valence electrons. Now how is that connected together? Well, once again, all of the group 1A elements, hydrogen, lithium, sodium, potassium, they can only be terminal atoms in any structure. So we'll calculate the difference in electronegativity. Electronegativity of nitrogen is 3.0, hydrogen is 2.1. The difference in electronegativity will be 3.0 minus 2.1, which is 0.9, and that is polar covalent. Let's take a look on our table. Notice for a non-metal to non-metal bond, anything above 0.4 is polar covalent. There are no ionic non-metal to non-metal bonds. They're either non-polar covalent or polar covalent, and the dividing line is 0.4 to 0.5. So the NH bond in ammonia is a polar covalent bond. Now the structure of this, well, let's see. I'm going to put nitrogen in the center because it has to share electrons with 3 hydrogens. Like so. Notice now that nitrogen has 8 electrons in its valence shell, so it's isoelectronic with neon, and each hydrogen has 2 electrons in its valence shell, so it's isoelectronic with helium. Now the structure, let's try and draw this a little more carefully. I'll show you the model in just a moment. One of the bonds comes out of the plane of the page and it's drawn as a widening wedge. One of the bonds goes into the plane of the page and that's drawn as a dotted line or a narrowing wedge. And then we draw a line in the plane of the page, and that means that's flat on the page, that straight line. And it has a non-bonded pair of electrons somewhere up here, taking up space. So they're actually 4 electron clouds. Those 4 electron clouds try and get as far apart as they can from each other in 3-dimensional space. And the bond angle for that is about 107 degrees. They're all about 107, at least the nitrogen-hydrogen bond angles are. Let's take a look at the model, and then we'll come back and look at this some more. So there's ammonia. What's the shape of that molecule? It's a 3-sided pyramid, if you will. The term is triangular pyramid. So can you visualize the shape here? This is one hydrogen coming out of the plane of the page. The dotted line is going into the plane of the page or behind the page. Then we have a hydrogen on the plane of the page, solid line. The molecular geometry of that, that's the arrangement of the atoms around the central atom, is described as being a triangular pyramid. So we see triangular pyramidal. We should count up the electrons in this. Bonding electrons, non-bonding electrons, valence electrons. Bonding are 6, non-bonding are 2. Total is 8. And that's what we figured out. We didn't gain or lose any electrons. That's good. Now these bonds are polar covalent bonds, so let's think about that. What does that do? So now that we know the shape, I'm going to draw dipole arrows pointing towards the more electronegative atom, nitrogen. These dipoles will not cancel. They're more or less additive. There'll be a net dipole in this direction. As a result, ammonia is a very polar molecule. Let me write here dipoles. They don't cancel. Ammonia is very polar. and therefore we predict it has high water solubility. In fact, it turns out it's miscible in water, which means soluble in any proportion. So we have a net dipole, negative at the nitrogen end, and these hydrogens are slightly, partially, delta positive. So this delta symbol is slightly or partially positive, and delta negative would be slightly or partially negative. Don't make me write that out again. Okay. Next on the list is carbon dioxide. Carbon dioxide, CO2, group 4A, group 6A. 4 plus 6 times 2 is 16 valence electrons in our structure. Okay, how is that connected together? We need to know that so we can calculate the difference in electronegativity. So let's see. Carbon, electronegativity is 2.5, hydrogen is 3.5. So is it connected like this or like this? I think that's only two possibilities. Why is the first one wrong? I got a feeling you know it's the second one, but why? The general rule is when either atom can be the central atom, both of these could have more than one bond, it's not like hydrogen, then whichever one is least electronegative is generally central. Carbon is less electronegative than oxygen, so it's more central. Now why is that? Well, less electronegative atoms are better able to share electrons. It's kind of like the drug dealer in the schoolyard. He's in the center and everybody's around him trying to get some drugs, right? Best able to share in the middle. A more practical way is simply to try and draw it. If you put carbon on the end, you'd never be able to get 4 bonds. Carbon needs 4 bonds. Can't do it. There's no such thing as 4 bonds on any atom, even carbon. So it's not possible. So carbon's in the center, so the difference in electronegativity for an oxygen to carbon bond is 3.5 minus 2.5, which is 1.0. So that's distinctly polar covalent. We're going to have some dipoles in this molecule. Let's draw the Lewis structure of it. We know that carbon has to be central. 1, 2, 3, 4. Oxygen has to be the terminal atom in this case. Now, I'm just going to quickly kind of sketch this, and I'll clean it up here in a second. Whoops. Let me redraw this. What's that going to look like? 2 double bonds on the carbon, right? Each oxygen gets a double bond. Notice in this structure that oxygen has 8 electrons in its valence shell in total. Both of them do, and carbon has 8 electrons in its valence shell, so everyone has a noble gas configuration. Let's count up our electrons and make sure we got it right. Bonding electrons plus non-bonding electrons make valence electrons. I've got 2, 4, 6, 8 bonding and 2, 4, 6, 8 non-bonding for a total of 16 valence electrons. Is that what we figured out? Yeah, we did. Okay, that's good. Now what about the shape of the molecule? Well, it's linear, right? This is a 180-degree bond angle here around the carbon. It's linear. That's its molecular geometry. Right, the arrangement of atoms around the central atom. What about these dipoles? Where are they? They point in the direction of the more electronegative atom. So there's a dipole going towards the oxygen, and there's another dipole going the other way towards the other oxygen, and these dipoles are equal and opposite. So dipoles cancel in this case. Unlike ammonia or water, where they combined. And so that means the molecule is nonpolar, even though it's got polar bonds. What that means is that it has very low solubility in water. Yeah, that's our prediction, and we are correct. I think it's less than 0.3%. It's pretty small. Let's take a look at an animation of carbon dioxide. Next molecule on the list is methane. Group 4A for carbon, group 1A for hydrogen. 4 plus 1 times 4 is only 8 valence electrons. Should be easy to draw. The electronegativity values 2.5 and 2.1. The difference in electronegativity for a carbon to hydrogen bond, 2.5 minus 2.1, 0.4. Now what is that? Remember on the table? That's an important point. For a non-metal to non-metal bond, 0.4 or less is so small it's considered to be non-polar covalent. That means that no matter how these are arranged, it's going to be a non-polar molecule. So carbon is in group 4A, 4 valence electrons. Each hydrogen brings 1 electron. You can just join them up like that, and now carbon has 8 electrons in the valence shell. Each hydrogen has 2 electrons in its valence shell, like helium. What's the structure of that? Well, it isn't as I've drawn it. I've drawn it on a flat piece of paper, but actually it exists in 3 dimensions. Let's take a look at the animation, then we'll come back and draw it. So how will you draw this on a 2-dimensional page? The bond angles in methane are about 110 degrees, as we'll learn later, but I've told you now. See, in 3 dimensions, the hydrogen atoms and their electron pairs can get farther apart than just 90 degrees, which is the best you could do on a flat piece of paper. They can get up to 110. You want to be able to draw this on paper. So we'll draw carbon. I'm going to show 1 hydrogen, a widening wedge coming out of the plane of the page, 1 going back into the plane of the page, and a hydrogen in the plane of the page, and another hydrogen in the plane of the page. And each bond angle here is about 110 degrees. See, on a flat piece of paper, the farthest you can spread these out is 90 degrees right angles. But in 3 dimensions, they can get farther apart than that. There's a name for this structure. The molecular geometry, the arrangement of the atoms around the central atom, is called tetrahedral. Tetrahedral. Tetra means 4, and hedron comes from the Greek means surface. So if you were to enclose this with 4 surfaces, well, you'd have 4 of them, and that's the shape that it is. Perhaps you've seen some dice that are tetrahedral. What about the polarity? Well, all the bonds are non-polar, so this is a non-polar molecule, which means that we predict insoluble in water or low solubility. We'd be correct, it is insoluble in water, as all hydrocarbons are insoluble in water. A hydrocarbon is any compound made of only hydrogen and carbon. Our next structure to draw is for that of ethane, C2H6. So that's group 4A and group 1A. 4 times 2 plus 1 times 6 means we have 8 and 6 is 14 valence electrons to show in our structure. We've already seen the difference in electronegativity for a carbon to hydrogen bond is 0.4, and that's non-polar covalent. Let's just draw it up. Here's the carbons. There's only 6 hydrogens in total, so carbon's going to have to share an electron with another carbon in order to give it 4 bonds. So now each carbon has 4 bonds. Each carbon has 8 electrons in the valence shell. It's isoelectronic with neon. Now, I'm not going to bother to draw this one in 3 dimensions. Let's just look at an animation of it. Notice that each carbon has 110-degree bond angles around it. The molecular geometry around each carbon is tetrahedral. It's a nonpolar molecule. It's insoluble in water. One last thing to check here. How many electrons do we show? Bonding plus non-bonding make valence electrons. Bonding is 2, 4, 6, 8, 10, 12, 14. And that's all. There are no non-bonding electrons, so 14 valence electrons is correct. All right, so the next structure we're going to draw after ethane is ethene. That's C2H4. Ethene. The common name for ethene is ethylene. Perhaps you've heard of polyethylene, the plastic made into milk jugs and plastic bags. Right, so let's draw ethylene. Again, we have 2 carbons, but we only have 4 hydrogens this time. That means carbon will have to have 2 bonds contributed by other carbons and only 2 from hydrogens. Now, how have I drawn this? This is going to be strange. How about 1, 2, 3, 4, and then a double bond for carbons. Let's draw that a little tidier. We'll have carbon to carbon double bond and then hydrogens here. How many electrons do we have? 4 times 2 plus 4. Looks like 12 valence electrons. Do we show that here? Bonding electrons, non-bonding electrons makes valence electrons. 2, 4, 6, 8, 10, 12. 0, 12, that's good. We didn't create or destroy any electrons. What's the structure of that? The structure is just what it shows. It's a flat molecule. And the reason is that the farthest that these 3 electron clouds, and this is one cloud of electrons, so there's 3 clouds of electrons around each carbon, the farthest they can get away from each other in 3-dimensional space is 120 degrees apart, like an equilateral triangle. So the molecular geometry around each carbon is a flat triangle. I'll write it out. So the molecular geometry around each carbon is a flat triangle. The term we use is triangular. Planar. Planar means flat. Some books say trigonal. Planar. I'm not sure the difference. They're the same thing, really. Let's take a look at an animation of ethene or ethylene. So there the bond angles are 120 degrees around carbon. Each carbon has 4 bonds, 8 electrons in the valence shell. It's a flat triangular structure around each carbon, triangular planar. C2H4, ethene. Alright, so just a couple more for this lesson. Let's try C2H2. Remove 2 more hydrogens. That's called ethene. And that'll have a total of 4 times 2 plus 2, only 10 valence electrons in it. I'll just kind of draw it quickly here. Each carbon will only have 1 bond to hydrogen. That means it needs 3 bonds to itself. So carbon forms a triple bond. So once again, there are only 2 atoms in the periodic table that can form a triple bond, carbon and nitrogen, and you're seeing it right here today. So number of valence electrons, we have bonding electrons plus non-bonding electrons makes valence electrons. So I have 2, 4, 6, 8, 10, plus 0 is 10 valence electrons. What can we say about the molecule? Well, we can say that the bond angle around the carbon is 180 degrees. It's a linear molecule, right? It's going to be nonpolar. It's a hydrocarbon. It's not going to dissolve in water to any appreciable extent. Okay, so the molecular geometry, I guess we could write that down. That'd be linear. Let's look at an animation of acetylene. Acetylene is the common name for ethine. Welder's fuel is acetylene or ethine. Let's look at an animation of that. Right, so there's ethine or acetylene. Carbon-to-carbon triple bond. Right, so try drawing now the structure of hydrogen cyanide. Hydrogen cyanide has the formula HCN. Group 1A, group 4A, group 5A. How many electrons? 1 plus 4 plus 5 makes 10 valence electrons. What's the way it's connected together? Is it HNC? Well, there's a couple ways you could figure this out. Let's look at the electronegativities. 2.5, 3.0. One of the ways you know is that the least electronegative atom is central, and that can't be hydrogen because it's always a terminal atom, so carbon is least electronegative. It has to be central. That usually works. The other way is you could just try and draw it, and you see it's impossible to give carbon a full valence shell without overloading nitrogen. Nitrogen can't have 5 bonds. This really isn't a possibility, is it? It has to be HCN. Let's draw that. So I'll just draw it kind of quickly. HCN. Nitrogen is in group 5A. It has 3 non-bonded, unpaired, single electrons in addition to its pair. All right, so here's the line bond structure of hydrogen cyanide. It's a linear molecule, right? 180 degrees. All right, is it polar? Is it soluble in water? What do you predict here? How would you do that? Let's calculate the difference in electronegativity. We've got 2 types of bonds. We've got a carbon to hydrogen bond, and we have also a carbon to nitrogen bond. We've already looked at this hydrocarbon. We know the difference is equal to 0.4, and that's nonpolar covalent. So no action down on the left-hand side, but what about the nitrogen to carbon bond? 3.0 minus 2.5, 0.5. It is polar covalent, which means there is a dipole, and it's only polar bonds that we draw these for. We don't draw them for ionic. We don't draw them for nonpolar. We draw them in the direction of the more electronegative atom. We're saying that nitrogen is more electronegative than carbon. So there is some polarity to this molecule. I'm going to say it is a polar molecule. What do you predict about its water solubility? I'm going to predict it is water soluble. Would be correct. It is water soluble. Notice that nitrogen has 8 electrons in its valence shell, and carbon has 8 electrons in its valence shell, and hydrogen has 2 valence electrons in its valence shell, so all of them have full valence shells. This is the most stable arrangement for those 3 atoms. There's one more we can draw. I'd like you to try this one. Draw the structure, please, of lithium hydroxide. It's group 1A, 6A, 1A. It's 1 plus 6 plus 1 is 8 valence electrons. Just check that we have that at the end. Check the electronegativity values. 1.0, 3.5, 2.1. Is that the way it's connected together? Yeah, it has to be, because both lithium and hydrogen are group 1A elements, so they can only ever have a single bond. They must be terminal atoms. So even though oxygen is more electronegative, it has to be the most central atom in this case. Let's draw that. Lithium 1 electron. Oxygen, 6 electrons. Hydrogen, 1 electron. What kind of bonds are these? Difference in electronegativity. We've already calculated the oxygen to hydrogen bond, I believe. Let's, in case we haven't, it's 3.5 minus 2.1 is 1.4, which is polar covalent. Those are going to share electrons, like in water molecule. What about the lithium to oxygen bond? What is that? Delta En for an oxygen to lithium bond is equal to 3.5 minus 1.0 is 2.5. What kind of bond is that? Take a look. That's a metal to non-metal bond. 2.5 is way up here on the ionic end of the scale. So that bond is ionic. Is that possible? Sure, why not? Why can't you have an ionic bond and a covalent bond in the same compound? So that means we're not going to draw a line. Many times students draw these structures. I see it too often. They go like this, and I'm like, oh no, that's not true, is it? What's wrong with that? Well, that's not a covalent bond. It's an ionic bond. So that means ionic bonds say that the metal donates or transfers the electron to the non-metal. So the correct structure would be Li plus OH. Now, how many electrons does oxygen have that are unpaired? Top and bottom, and it's got the original one plus the one it took from lithium. Let me color it here. Let's just say, how about green? Will this work? If I make this electron green, so here it is now. Right, that's been transferred. Now, what's the charge on the oxygen and the hydroxide? Well, the hydroxide has to be minus. Plus and minus makes a neutral compound. This is a good point to differentiate between how many electrons an atom owns versus how many it shares. In the case of the Lewis symbols of the atoms, lithium owns 1 electron, and it's neutral. A lithium atom owns 1 electron. But in the lithium cation, it doesn't own any electrons in the valence shell. And so, because it has 1 less electron than the neutral atom, than the neutral element, its formal charge is plus 1. So I'm giving you a new term here. It's formal charge. So in a structure, we like to assign charges to atoms. It's actually important. So the formal charge is determined by comparing the charge of a species in a structure compared to the neutral atom. The neutral atom of lithium owns 1 electron. Anytime lithium owns 1 electron in the valence shell, it must be neutral. This lithium doesn't own any, so its formal charge is plus 1. Let me write that here. Plus 1 formal charge. What about the hydrogen on the right? I know that it shares 2 electrons. Let me draw in what it's sharing, 2 electrons. But how many of those does it actually own? So for that, what we do when electrons are being shared in a covalent bond, we simply divide that electrons between the 2 atoms that share them. So we'll say that hydrogen only owns 1 of those 2 electrons. So let me divide it this way. Okay, of the shared pair, 1 of them belongs to hydrogen and 1 belongs to oxygen. So how many electrons does hydrogen own this way? Well, it owns 1. And on the Lewis symbol of a hydrogen atom, it owns 1 electron, so this is neutral. The formal charge of hydrogen in OH is 0. What about the oxygen? How many electrons does oxygen share, and how many does it own? You can see that it shares, let me draw some green dots in here, it shares 8, 2, 4, 6, 8, where I'm drawing the green line. But how many does it actually own? Let me draw that in red. It owns half of what it shares and all of what it doesn't share. This is what oxygen owns. It owns all of what it doesn't share and half of what it shares. So oxygen owns how many atoms? So oxygen owns 2, 4, 6, 7. It owns 7 electrons. What is it when it's neutral? It owns 6 as a Lewis symbol. So the formal charge of oxygen is minus 1 because it owns 7 electrons in the structure. Even though it shares 8, it owns 7. Formal charge is the charge on an atom in a structure. You determine it by adding up all the electrons that an atom owns. Compare it to the Lewis symbol. The Lewis symbol of oxygen is neutral. It owns 6 electrons. This has a formal charge of 0. But in our structure, it actually owns 7, 2, 4, 6, and half of what it shares. So all the electrons that are not shared belong to the atom, plus half of what it shares. So think about a water molecule. Here's a water molecule, right? How many electrons does oxygen actually own now? It doesn't own 7 anymore. It only owns 6. All of what it doesn't share and half of what it shares. So the formal charge of oxygen in water is 0, but the formal charge of oxygen in hydroxide is -1. And so when you draw the structure of hydroxide, we now know that the negative charge is not on the hydrogen, but rather it's actually on the oxygen. The hydrogen is neutral. This is described on page 110. Formal charge, and it's hydrogen owns 1 electron, half of what it shares. So its formal charge is 0 because it's the same as the neutral element. It owns 1 electron in its Lewis symbol. In hydroxide, oxygen owns 7 electrons, all of what it doesn't share and half of what it shares. That's 1 more electron than the neutral uncharged atom. So its formal charge is -1. This negative charge belongs to the oxygen. In the case of the sodium cation, it owns 1 less electron than the neutral atom, and therefore its formal charge is +1. It's an important distinction. So even though oxygen has 8 electrons in the valence shell, it's isoelectronic with neon, in terms of its formal charge, it's not neutral, it's -1. Even though sodium cation has 8 electrons in the inner shell and none in the valence shell, it's isoelectronic with neon, but it has a formal charge of +1. And this looks like a good place to stop in this lesson on drawing Lewis structures of simple covalent compounds.